Thank you. So today the plan is to try to unite all the ideas of the two previous talks. We will see how much I can accomplish with them. So let me remind you the running narrative of these lectures. What we are interested in are these topological mirror tests, the agreement of certain Hodge numbers of first moduli space of Higgs bundles, the Hitchin systems, and in the other case, these character varieties. And then I will list three problems which have been bugging this project from the beginning, in fact. And then today I will offer a solution to these problems. So we have always fixed the genus G smooth projective curve, complex, so it's just a Riemann surface. We will have rank n bundles, we will consider GLN, and we will consider degree D bundles and D-twisted character varieties. So in the first lecture we studied the total space of the SLN and PGLN Hitchin systems, SLN moduli space of stable degree D, SLN and PGLN Higgs bundles. And in yesterday's lecture we studied somehow these varieties in different complex structures. In the complex structure J, the variety, these complex manifolds can also be thought of as varieties, and the corresponding algebraic variety structure which was relevant for us was the moduli space of, well, the moduli space of representations or characters of the fundamental group of the Riemann surface into SLN and PGLN. So again, the important thing is that these varieties thereby share the same cohomology. They are canonically identified, but they have different Hodge numbers. The weight filtration, for example, I defined yesterday, or not defined, but mentioned yesterday. They are going to be trivial for the Higgs moduli spaces. They are pure weight filtration. That means the weight really agrees always with the degree. But it's not the case for the character variety, where the weight filtration is really mixed in every given degree of the cohomology. So this is really different Hodge numbers we are talking about. So I offer two topological mirror tests to try to find proofs, topological proofs for the mirror symmetry we observed between generic fibers of the Hitchin map. So one was the agreement of Hodge numbers of the SLN Higgs bundles with the corresponding, but the stringy Hodge numbers for the PGLN Higgs bundles, which is an orbifold. So that was one set of conjectures. I mentioned that in the original work we could do n equals 2 and n equals 3, and until recently, in fact, it has been open, so we didn't know any larger n, and then today I will report the solution n equals a prime. Then the second set of conjectures we had yesterday concerned the Hodge numbers, or rather this Serre polynomial, this E polynomial, which is alternating some of these Hodge numbers, agreement for the character varieties. So we took the SLN character variety, the representations of the fundamental group into SLN. We took its Serre polynomial, and then we found that when n was a prime by arithmetic calculations, we managed to show that it was the same as the stringy Serre polynomial of the PGLN character variety, which was an orbifold. So this is the picture which existed until a few years ago, and it really raises a lot of question marks. So the original question mark I already mentioned at the end of my first talk is the puzzle of why we are seeing the same Hodge numbers when in mirror symmetry we would like to see some kind of mirror transformation of the Hodge numbers. So somehow a symmetry is missing, like in the case of a compact hyperkiller manifold, for example, the K3, we have seen this inbuilt symmetry in the Hodge numbers of the K3. Somehow that was explaining why we are seeing the same Hodge diamonds on the two sides. But we don't see this for these Hodge numbers. In fact, the Hodge numbers here have no symmetry at all. The second question really concerns this very fact, which you can already notice in this slide that we have two conjectures. And then the two conjectures are really different. As I mentioned, the Hodge numbers here are pure, Hodge structure here is pure, and here it's far from being pure. The E polynomials, the SER polynomials are really, really different. So why do we have these two sets of conjectures? Which one really is the one which reflects the mirror symmetry which we would like to understand? So that was also an embarrassing question, which I could have been asked after lectures on this. And the last one is maybe just to explain the relevance of these conjectures to the geometric and the classical Langlands program was also a mystery. The geometric Langlands program, or rather S-duality, was always a question of why mirror symmetry wants us to have these topological mirror symmetry conjectures. That was not clear at all. What's the mechanism to go from these physical duality ideas, or in other words, this geometric Langlands program, and then this agreement of Hodge numbers? That was not clear. And then, of course, the nice thing always would have been if there was a relation to the actual classical Langlands program, to actual number theory. And then at the end, I will offer some good news in that direction as well. So in order to start, what happens when one looks at these Hodge numbers of the character varieties, unlike in the case here, where we will notice that there is going to be an extra symmetry, and that's going to be the starting point of what's going to happen today. So let me show you in a practical example, in a very small example, when the genus is 2, and then is 2, and we consider the SL2 character varieties. And you remember what we are doing, we calculate everything with these character formulas along the irreducible characters of SL2FQ. And then what we find, in this case, that we find that the E polynomial, where Q is going to be equal x times y, is going to have this shape. And of course there is one obvious thing which everyone notices when looking at such a polynomial, that wow, this is palindromic, meaning that it reads the same way backwards. So there is a symmetry in the coefficients of this SER polynomial. So that was always very surprising when we first saw it, when we first did this calculation, but this persisted in every single example. If you calculate the SER polynomial of a character variety, you always see the same kind of palindromicity. You can formulate this palindromicity in this very attractive form. It looks like a functional equation, which is not really an accident, because we will see later that this will, at least conjecturally, underlie some symmetry of the homology, which is a little bit like Poincare duality. And of course, Poincare duality has a lot to do with functional equations in number theory. So anyway, so you have this functional equation which is always shown in every single example we calculated, and then you can think about why. When you do this character formula sum, why do you see this symmetry? And the reason is that actually the irreducible characters of finite groups of Lie type come in pairs. So there exists a duality theory among characters of irreducible characters, which is a nice general theory for every finite group of Lie type. Alice Curtis found this duality which roughly says this, at least on the level of the dimension of the characters, that as functions of Q, you can get one from the other by looking at it backwards. There is some K which depends on the group. So when you look at this, and then when you look at your character formula calculation, then exactly this duality will be responsible for this overall functional equation, this palindromicity of these polynomials. Anyways, it's very nice. There is a deep explanation of why we see this palindromicity, and then you can start to think about the symmetry we are missing, right? I already mentioned that we would like to see in these mirror symmetry stories an extra symmetry, and then the vague hope at this point was that maybe this symmetry is going to answer it. It's not quite that simple, as we will see, but indeed you can start to think about maybe there is a deeper symmetry among the Hodge numbers. If you remember, these SER polynomials were a generating function for alternating sum of Hodge numbers, and in this case it was a non-trivial alternating sum of Hodge numbers, and you can wonder if this symmetry persists when you look at the Hodge numbers themselves, and it turns out that in fact that is true. There is, conjecturally at least, you can pair the Hodge numbers of this variety, and they are the same. And in fact, not just that they are the same, they are somehow connected by something which looks like a hard Lefschetz theorem. So that made us conjecture that maybe there is a deep reason for this symmetry in the Hodge numbers, or what you can really observe on these Serre polynomials, the polydromicity of the Serre polynomials, that can be explained by a hard Lefschetz kind of result, or conjecture in this case. So what you notice is that you can define a what we call curious hard Lefschetz conjecture by taking a cohomology class in the character variety of a given weight. The weight is very important because the weight tells us how much further up we can go. We have to see how far away we are from the middle weight, and then we can go up exactly that much. So the resulting, the dual thing, will have a degree which depends on the weight of the class. That's why we couldn't see, for example, this symmetry in the original Higgs moduli space. You needed this extra structure, the weight filtration. And then, in fact, there is a class, a unique class or a one-dimensional space. In fact, H2 is one-dimensional. But this is a funny class for a hard Lefschetz theorem because the class is not type 1,1, but the class is type 2,2. So that's why we partly call this a curious hard Lefschetz theorem. It's not the kind of hard Lefschetz theorem you've seen before. It really messes up degrees and weights. That's why was it not seen in the Higgs moduli space case. So this remained really a puzzle, but it was a very nice conjecture. Now, we at least for the character varieties, we found this extra symmetry which might be relevant for the mirror symmetry conjecture. Of course, if you have a conjecture, it's not enough. You really want to have some results as well, and in fact, we could prove this result for n equals 2, which is already a non-trivial calculation. When n equals 2, previous work with Michael Adams, we completely described the cohomology ring of these varieties explicitly by generators and relations. And from that explicit description, it was hardly non-trivial, but I could prove with Fernando that using this extra structure, the weight filtration, which you can easily see in the ring, you will have exactly this isomorphism in the cohomology ring. So it was a brute force calculation, but it proved that there exists, at least for NS2, this highly curious hard Lefschetz theorem. That was exactly a good sign that maybe these kind of symmetries persist. But somehow the mirror symmetry really makes sense for Hitchin systems. That's how the physics tells us. So the question was, or it could have been, it wasn't really my question, although there were some formulas which I already attempted trying to compare Hodge numbers of the character variety and the Higgs bundles, but I didn't have a conceptual way to think about it. But what happened instead is that my colleague Fernando Rodriguez Villegas gave a talk in Princeton where he mentioned this result or this conjecture in general, and in the audience was Mark De Cataldo and Luca Migliorini, who suddenly noticed that they have seen hard Lefschetz theorems of this type. And that's probably the reason I'm actually here, because of this conjecture and that coincidence in Princeton, because then Mark and Luca later contacted me, and then we started to work on a conjecture which will show up very soon. But to understand why they became so excited about this conjecture, we have to see their experience with a different setup where there was a non-trivial filtration on the cohomology of a not necessarily projective variety, which exhibited a very similar kind of hard Lefschetz theorem, when somehow which degree you ended up depended on where you were in the filtration, not just in which degree you were, which is unlike in the hard Lefschetz theorem. So let me show you their construction. So that's the perverse filtration, and it is attached to some completely different geometrical setup. So it is attached for the cohomology of the total space of a proper vibration between complex varieties. Maybe you can concentrate on the case when X is smooth and Y is affine, because that's really going to be the case we will have, but the theory is much more general. In fact, they just say that perverse filtration is really already present in the papers of Beilinson, Bernstein, and Deligne, about where they talk about the perverse sheaves and the decomposition theorem. Indeed, you can define this perverse filtration by just saying that if you push forward the constant sheaf, then you decompose it according to the decomposition theorem into perverse constituents, which is not a unique decomposition, but when you take homology of this decomposition, it will induce a filtration, which will turn out to be unique, a well-defined filtration you get by studying the decomposition theorem. So their observation was, at least one of the observations, that you can actually give a very down-to-earth definition of the filtration without mentioning the frightening words of perverse sheaves. And that's exactly the kind of things I can work with, so it was very good for me. So they are proving the following result about this perverse filtration, which is probably the best for us to think about. So in the case, again, when the total space is non-singular and the base is affine, they prove that you can understand the perverse filtration by testing your filtration along a flag of subspaces inside the base. So you have this affine variety, you take a generic hypersurface, inside that you take another generic hypersurface, etc. You have this flag for every dimension, you will pick one guy, and what's important in this flag, it has to be generic, and they define what this means. Roughly speaking, what it means that they somehow have to be orthogonal, that's not the word. No, that's the word. What was it? Transverse. That's very good. So transversal to the various loci, discriminant loci of the vibration. So this is a non-trivial definition, but anyway, imagine that you just take some generic flags, and then once you manage to do that, then what you have to do, you have to test your cohomology classes for these elements in the flag. So you take yi, you take the total space of the vibration above that yi, and then you restrict the cohomology classes in the total space in X into that subvariety. And then the only thing you are looking for, which are the classes which go to 0. And that's exactly going to be one element in the perverse filtration. It's a very neat definition. Basically, the only case it's easy to work with is the general point. So you take the generic fiber of your map, you restrict the cohomology classes from the total space and see which ones go to 0. That's going to pick up one part of the perverse filtration. Anyway, it's very nice. If you take this definition, of course, then it's not going to be that simple, but in the original definition using the decomposition theorem, in fact, this was probably one of the motivations behind the decomposition theorem. They were thinking about trying to understand Lefschetz theorem in families, and then this is a very good example of this relative Lefschetz theorem. So you have these families of maybe sometimes singular varieties. You have this smooth total space, say, and an affine base, and a proper map between them. You define a perverse filtration like that, or better maybe with the original definition. And then the relative Lefschetz theorem, now which is not a conjecture, says exactly the analog thing that it did for us in the conjecture wave filtration case, that there is a very similar kind of Lefschetz theorem. That is, you have to know which part of the perverse filtration you are in, and that will determine as how much you can go up in both in degree and perversity. And that is going to be an isomorphism. But now alpha, in fact, is going to be something more reasonable for a Lefschetz class. It's going to be a relative ample class. It will be, in particular, 1 plus 1, type 1, 1. So it's really, it's not that, nothing that curious here. But of course, it's a really non-trivial result. If you just take this as your definition, why would it satisfy relative Lefschetz? But that's their theorem. Okay, so that was what they knew when they heard about our conjecture or our theorem in the NS2 case about the wave filtration, and they said, wow, it exactly looks like this relative Lefschetz theorem. So maybe there is some kind of perverse filtration around in our picture which might explain the curious Lefschetz theorem. And indeed, it took them several months to come up with the obvious guess. But after several months, they contacted me with this conjecture, which then we started to believe is that maybe you have to take the Hitchin map. So you take now the Hitchin map, if you recall, was a map by taking the characteristic polynomial of the Higgs field of the Higgs bundle. This was in the case of, say, this twisted GLN Higgs bundles, for example, it was a non-singular, it was a smooth total space, it was a proper map, it was a very important property of the Hitchin map. It was proper over an affine base. So we could actually consider now the perverse filtration on it, maybe with the definition that Mark and Luca are giving. And you have a filtration there which is going to satisfy the same kind of Lefschetz theorem that we conjectured with Fernando to be satisfied by the character variety. But remember, the character variety and the Higgs moduli space is canonically diffeomorphic. They have shared canonically the same homology. And then you have one filtration in one hand, the weight filtration, which somehow satisfies this extra symmetry. And you have the perverse filtration on the other hand, which satisfies the same symmetry. So the obvious guess now is, of course, that the two filtration are the same, and indeed that's what now we are conjecturing, are the same under identifying the cohomologies in the canonical way by the non-abelian-Hodge theorem. So this is really surprising on the surface, because one filtration somehow measures the topology of the Hitchin map, the singular fibers, the cohomologies. It's something topological in nature. On the other side, you see the weight filtration on the character variety, which is Hodge theoretical at least, but for me it's even more arithmetic. It somehow sees the weight of the Frobenius section, the eigenvalues of the Frobenius section on eta cohomology. So this is really a surprising conjecture for us at least. And then, of course, if I am saying a conjecture, I should say a theorem as well, and fortunately now I can. We managed to prove for GR2, PGR2 and SR2, three independent and different in their own right cases. We managed to prove now this conjecture that the perverse filtration agrees with the weight filtration. So this proof is actually somewhat similar from my perspective to the proof of the Lefschetz theorem for the curious Lefschetz theorem for the character variety, in that it uses literally every known property of the cohomology of these rank 2 Higgs moduli spaces. It's really amazing to me that it's really literally everything we discovered is known, is used here. And besides that, of course, you have to work very hard on the perverse filtration side. The weight filtration was completely understood in the NS2 case in the work with Fernando. And then now the job was to show the same about the perverse filtration, which turned out to be a highly non-trivial business. So in particular, what the calculations that we were led to do were very surprisingly, were very, very close to, well, the results we were getting by explicit calculations were really reflecting some much more general results of Engel in his proof of the fundamental lemma in the Langlands program. So that was a surprising accident maybe, because we were really just thinking about this conjecture, but then you are interested in the perverse filtration on the moduli space of Higgs bundles. You end up thinking about the monodromy of the Hitchin fibration, and then that's exactly what Engel does, although in a much more conceptual way. We are really doing down-to-earth explicit calculations, and the surprise actually for the experts may be that these calculations are possible to be done. So that's already a very good point where you could say that these kind of conjectures, at least these structures, are relating to explicit results in the classical Langlands program, but we will see later that there will be an even closer connection to Engel's work. So now what I can do, I can now solve two of my problems, which I started with. So what we can do now is that we can discover this extra symmetry which we were missing from the first lecture. So we can actually find the extra symmetry why the Hodge diamonds are actually really mirror to each other. It actually, we are going to consider not just Hodge diamond, but maybe Hodge pyramids or some three-dimensional array of numbers, because we will include one more filtration, the perverse filtration. And the second upshot will be that in fact we can now take a single conjecture which will specify to the two previous conjectures. So we will have a single conjecture about topological mirror symmetry, and we will have the missing symmetry as well. Okay, so what is, I mean, it's probably easy to guess now what you should do in order to understand where this extra symmetry is coming. You have to include in your Hodge numbers the perversity of the classes. So that's one of the results of Mark and Luca, is that the perverse filtration is compatible with the Hodge structure. So in fact, you can take the graded pieces of the perverse filtration and look at the Hodge numbers there. The Hodge numbers in the case of the moduli space Higgs one is always pure, so I plus j always equals the degree. And so we have now this three-variable polynomial generating all the Hodge numbers, but now we are also remembering the perversity of the classes. So instead of a Hodge diamond, now as I say, probably it's a Hodge pyramid, or I haven't really thought about exactly what geometrical shape these numbers are going to be. We have, for example, no Hodge numbers above middle dimension. So anyway, so that's really the idea, is that we have to include the extra structure and then the symmetry appears by itself. But before we talk about the symmetry, let me mention that now this polynomial in three variables should be a common deformation of the Serre polynomials of the Higgs bundles and the Serre polynomials of the character variety. Because if I forget about the filtration, the perverse filtration, then of course I get back my usual Hodge numbers. We are taking here ordinary cohomology, actually. That's the reason I have to take a Poincaré duality kind of business, because it's ordinary cohomology. In our work, it's important to work with ordinary cohomology because we study the ring structure, so it's probably natural to work with that. But when you work with Serre polynomials, it's natural, you have to work with compactly supported cohomology because that's going to be the additive one. Anyway, so you have to do this little Poincaré duality, but that's not a big deal. So this polynomial, of course, specializes to the previous Serre polynomial for the Higgs moduli space. But also, if you believe the conjecture for any n, but definitely for any plus 2, when we prove this polynomial will also specialize when you forget about the x and y to just the weight filtration on the character, or the perverse filtration, which should be the same as the weight filtration. So eventually, we should get these formulas of the Serre polynomials of the character varieties appearing again. If you remember, they have explanations, or they have formulas by finding the character tables of finite use of Lie type. So this is somehow the real Hodge numbers one have to consider in these kind of mirror symmetries, because then we have the two mirror symmetry conjectures can be unified, and also we have this inbuilt symmetry in these Hodge numbers. The relative Lefschetz theorem translates to this functional equation, this nice functional equation. It says that these three indexed Hodge numbers are coming in pairs, and they are very nicely related by a relative Lefschetz kind of connection. And then now, putting everything together, the proper version of the unified topological mirror symmetry conjecture should take this form. What one should have is that the perverse Serre polynomial of the Hitchin system, I forget about these d's, they shouldn't be here, but they really remember the degrees, which I usually omit. Anyway, should agree the stringy perverse Serre polynomial, which you can analogously define for the orbifold of the PGLN Higgs moduli space, but somehow in the opposite degrees, and then doing relative Lefschetz say on the right hand side. This should make it agree with just the stringy perverse Serre polynomial of the orbifold. So that's really now the right definition for the topological mirror test. You see the symmetry, the mirroring phenomenon. You see that there is an inner symmetry. So in fact, that specializes to the agreement of these Hodge numbers. So okay, so that's very good. So before I am solving the last question, explaining why you would actually need to consider this as your topological mirror test, how it comes from geometric Langlands, which I will be very brief about. I'll show you an example, exactly the example I showed in the first lecture, where things are very explicit, where we can see how this extra symmetry appears from nowhere, really, because there is no symmetry to start with, and then suddenly when you include the perverse filtration, it will arise. So let me take the same example, which is something which is not included in the conjectures we have, because it's a parabolic Higgs bundle moduli space, but unfortunately none of the spaces appearing are surfaces where things can be drawn. So you have to go to parabolic ramified version of these conjectures, and then everything will be fine. So the example we have is the moduli space of SL2 parabolic Higgs bundles on a given elliptic curve with one parabolic point. Okay, I mean you can go on exactly to define this, but you can do this. And then it turns out to be a surface. The total space is going to be a surface. The base of the Hitchin map is going to be half of the dimension because it's an integrable system. It's going to be one-dimensional. It's going to be an affine line. What it is going to be, then it's an integrable system. Generic fibers will be tori, will be actually varieties, will be elliptic curves. In fact, they will always be a copy of E. So elliptic curves generically outside zero, but over zero we will have a single fiber of type D4 hat. So the picture is this. Here you have the complex plane. Over zero you have these configurations of P1s along the shape of a affine D4 thinking diagram, and the generic fiber is always the same elliptic curve E. So that's the fibration we have. Then
sorry, the picture is supposed to say that they're simply connected, or
it is simply connected because it contracts to the middle fiber, which is simply connected. So every fiber is a torus except the one in the middle, which is this.
So is this topologically the same as T2 times the plane mod C2?
Yeah, I come to that in the next slide, yes. But first I just want to give you roughly what it is, and then later I will explicitly tell you what this, how exactly what you're saying is going to be the case. But you see, now you can think about first of all, what's H2. So first, easy to see H2, the compactly supported will be given by these cycles, these compact cycles. So it's going to be 5-dimensional. So will be by quantum duality ordinary cohomology will be 5-dimensional. And so the question is, what's on this this 5-dimensional space, what's the perverse filtration? So we are going to test it by Markens Luca result by restricting to this flag, which in this case can only have one non-trivial element, namely a generic point. So we are going to take a generic point, we are going to restrict from the total space to these tori, and then think about what's the kernel of this map in here. So we are restricting from ordinary cohomology of the total space to the second cohomology of the elliptic curve, which is the generic fiber, and we want to know what's the kernel of this map is. And the point is that if you take a compact cycle like that, then you think of this as a non-compact cohomology class, it's clearly going to restrict trivially to this guy, because it's just geometrically disjoint from that. So everything which comes from compact cycles will actually go down to zero, and then the result then is going to be that the kernel of this map is going to be exactly the image of compactly supported cohomology in ordinary cohomology, because it's going to be 4-dimensional image. You can calculate the intersection form of compactly supported cohomology. You have the Cartan matrix of the D4, affine D4, so the rank of that is 4. So you will have a 4-dimensional space, and that's exactly what you want, because of course alpha, the relative MPO class, will restrict non-trivially. So there will be a 1-dimensional class which does not restrict trivially, but a 4-dimensional space is going to restrict to 0. So therefore, we see that this will have dimension 4. This part of the, so you have 4-dimensional perversity 1 part of H2, and then a 1-dimensional perversity 2 part, namely alpha. Okay, so from this we see how the symmetry arises, right? So the Hodge numbers, the Serre polynomial of the space is this 5 times xy. We are complexly supported now, so this 5-dimensional compactly supported space, and the 1-dimensional H4. So that's non-symmetry. But when you include the perverse filtration, then suddenly the perverse Serre polynomial is going to become symmetric. We will have a four-dimensional perversity 1 part of H2 and a one-dimensional perversity 2 element in H2, namely alpha. And this is what exactly we need for relative Lefschetz, right? Because if I apply alpha to this class, I'm going to want to end up here. So that's going to be in the non-trivial or relative Lefschetz. But what we see is the symmetry appearing when we include this new filtration. And indeed, you can do now the character variety calculation along the lines of yesterday's lecture. You can calculate the E polynomial, the SER polynomial of the character variety, and you are going to get this symmetric expression as expected from this conjugate calculation 1 plus 4q plus q squared. And then finally, we see that this is now symmetric. You have this polynomicity condition, so the relative Lefschetz tells you that this functional equation is satisfied. So that's how this extra symmetry arises. And in the next slide, in the same example, I'm going to tell you how the mirror symmetry will work in this case. It will be, as by surprising accident, we will have a conceptual understanding of why the mirror symmetry is true. So, example for the unified topological mirror symmetry. Now I'm going to tell you exactly along the lines of what Wood was suggesting. What is the construction of this space, how this this surface arises. So you take the action of Z2 acting on the two groups, additive groups, the elliptic curve and the complex numbers by the inverse, taking x going to minus x. We take the product. On this we have the diagonal action of the inverse. When you take the quotient, you will have four orbifold points. You have one fixed point in C, but you have 4 points exactly. The order 2 points in the elliptic curve will be the 4 fixed points of this section. So overall in the product you will have 4 fixed points by the Z2 action. You blow up those 4 points. That's going to be our surface, and the map is just going to be the projection to the second factor, and C mod Z2 turns out to be canonically isomorphic with C. In the generic fiber, you will just see a copy of E, and over 0, we divided E part by the Z2 action. It's going to be a P1 with 4 orbifold points. We blew up those 4 points, and that's exactly the source of this configuration of the 4 hat P1s. Now I'm telling you this because now we have to do a further orbifold quotient of this. Namely, we will have an action of the Klein group, which is going to be just the 2 torsion points in this elliptic curve act on this total space. And the action really will be induced by the action on this elliptic curve. And then when you think about how this acts, the quotient is of course going to be our orbifold quotient, the PGL2. The question is, which you have to understand, how this finite group, the Klein group, is going to act on this middle configuration. And the answer is that it's going to act transitively on these 4 P1s, and then in the quotient you will see 2 P1s glued together, a copy of the original middle one, and the 4 glued together. So you will have an even configuration for the orbifold. But on one of the, in the middle component, you will see 3 more orbifold points appearing. And the point is that in this case the orbifold has a Crepon translation, unlike in any of the other examples I talked today. And if you resolve those 3 points, you are going to get back exactly the same kind of elliptic fibration we started in the first place. Basically, you will get back the same variety. So it's a very surprising phenomenon. You divide a surface by a finite group, and then the surface itself will be isomorphic to a Crepon resolution of this. And that, of course, should explain the mirror symmetry in this accidental situation. By the result of Kontsevich's motivic integration, you can prove that the stringy numbers of an orbifold agree with the Hodge numbers of the Crepon resolution. So the original topological mirror test in this accidental case can be geometrically explained. But very similarly, you can extend it to have an agreement of the perverse set polynomials, and then including the relative Lefschetz theorem, you can reformulate everything to give the conjecture version of the mirror symmetry.
Do these moduli spaces admit complete hypercalorimetrics?
Yes. So there are some other examples, and this is the most general example, but if E might have some Z3, I think 1 for E, 60, 70, 80, but we'll also have an example. But those are special elliptic curves, and then you will have a complete hypercalorimetric on these surfaces. It will be some kind of parabolic Higgs bundle picture. It's very similar to this one. So this concludes at least this example for this unified topological mirror symmetry. And in the last slide, I will give you in a quite dense way at least some indications for the answer to the last question. The main question maybe is what's exactly the mechanism which should induce this mirror symmetry conjecture now in this more refined form. And then the other thing I will offer an answer or a conjecture maybe is how it's related really to Engel's main result, main geometrical result, which implies the fundamental lemma. So this is unfortunately going to be only one slide, which was actually one lecture last week in Oxford, but it's going to be somewhat dense. So the talk in Oxford was called From S-duality to the Fundamental Lemma. It's really, it's very nice, this idea of S-duality in physics, because it starts from a very visible duality theory, the so-called electromagnetic duality in Maxwell's theory of electromagnetism. So if you look at the equations, even without really understanding the differential geometry of Maxwell's equations in vacuum, then you already notice the obvious thing that it is symmetric again there is an obvious duality by replacing the bold E, the electric field, with minus of the magnetic field, and these equations are symmetric with respect to that. So that's the source. This electromagnetic duality is the source of S-duality, which in the late 70s was studied, and by Montonen and Olive extended this duality. You can think of this Maxwell's theory as a U1 gauge theory, so it's really just connections on a U1 bundle in 4 dimensions, on a 4-dimensional manifold, say R4. And then their question was how you would extend this kind of duality theories to non-abelian gauge groups. So you take Yang-Mills theory now with a non-abelian gauge group, and then what they understood is not enough just to take pure Yang-Mills theory. You have to take a supersymmetric version of that, and the high supersymmetry of that n=4 supersymmetry is going to be the right theory, which should exhibit this same kind of symmetry. I forgot to show you the full symmetry. And this, then Monton and Olive generalized this to this non-abelian setting. The amazing thing, in fact, that they already noticed that the gauge group of one theory should go to the Langlands of the dual gauge group. So that was already an early hint in 1978 that this S-duality should be related to Langlands duality. And then it was then noticed by Kapustin and Witten, of course, in 2006, that this appearance of Langlands duality may not be that by just accident, because they were arguing that if you reduce from 4 dimensions this S-duality, you reduce it to 2 dimensions, then one thing is that the Yang-Mills equation will become these self-duality equations whose solutions are exactly these Higgs bundles. So they found that in the physical sense, this 4-dimensional S-duality will reduce to exactly homological mirror symmetry in the sense of Kontsevich between Hitchin systems for Langlands dual groups. So Langlands dual groups appear because they appear in the original S-duality. You reduce both sides by 2 dimensions. Everything is defined over, say, R4, and you take the fields to be invariant under 2-dimensional translations. And then what you get are the 2 Hitchin self-duality equations. Then the solution space will become the moduli space of Higgs bundles for Langlands dual groups. And then what they noticed is that this physical S-duality should exactly be this homological mirror symmetry. If you're a mathematician, then you can think of the work of Kontsevich. You can attach categories to the 2 sides. And now we somehow think that this categorical equivalence coming from this homological mirror symmetry is really how geometric Langlands program should be thought about. But without really going into any of the hard details here, let me just tell you, in one limit of this duality, it is expected that things should become much simpler, and then the duality should be generated by what's called a fiber-wise Fourier-Mukai transform. And that's really the starting point of connecting the real of the physics to the kind of observations we made about Hodge numbers. So what is this Fourier-Mukai transform, very briefly? So if you have any abelian variety, you can take its dual, which turns out to be the degree 0 line bundles on your abelian variety. It turns out to be a fine moduli problem. You will have a universal bundle, the so-called Poincare bundle, the product of the abelian variety with its dual. And then you can use this Poincare bundle to transfer sheaves from one coherent sheaves from one abelian variety to the other. Pull it up, tensor with the Poincare bundle and push it forward. You must have seen this many times. And then Mukai proved that this is an equivalence of categories. Okay, we are topologists, or we are interested in the cohomology. You can think about how this acts in cohomology, and that's going to be highly non-trivial action. It looks like it's going to be Poincare duality, at least in the degrees, but much better to think of it's more like a Hart-Lefschetz theorem. Because that's what then you manage to do. You can go on, and in this Hitchin fibration, now you have these pairs of dual abelian varieties in the regular locus. You can try to extend this fiber-wise Fourier-Mukai transform to the singular fibers. This actually was exactly the question asked by Helen in the first lecture. Can you do this? And then it seems that now you can do this. There is a recent work of Arinkin, who works with any integral curve, plane curve, and he proves the autoduality of the compactified Jacobian, which seems to be possible to extend for this SL and PGLM situation, and you should have an equivalence of derived categories for these integral fibers of the Hitchin map. And so then it seems that you can actually extend fiber-wise Fourier-Mukai transform into what's called the elliptic locus, where the fibers are integral, that is reducible and non-reduced and reduced. Okay, and then the question is, you have this fiber-wise Fourier-Mukai transform, which on the first side will act on derived categories, but you can think of the action in cohomology. What does it give on cohomology? And this is some observation we made with Mark and Luca, that in fact, in order to understand the effect of Fourier-Mukai transform, this is only in the regular locus when everything is nice and smooth. In that case, you can understand that the cohomology is going to be mixed up exactly using the perverse filtration on the two maps. So the perverse filtration is crucial to understand the effect of the Fourier-Mukai transform on cohomology. In fact, what we prove over the regular locus, that the degree you will end up is exactly the expected degree in this topological mirror symmetry. And indeed, that's the idea now, that you can actually prove topological mirror symmetry by this fiber-wise Fourier-Mukai transform. The first step is to extend everything over the elliptic locus, where integral spectra occurs and integral fibers are present. Use Arinkin's work to identify or to have the Fourier-Mukai transform. And then what we are aiming to prove is that this kind of action on cohomology extend exactly like this. So perversity will go to the opposite perversity, and the degree will change accordingly. And then on this side, you must see the stringy cohomology. I mean, I put here stringy, which is a cheating, because this is the regular part, and this is still non-singular even on the PGLM side. It's going to be interesting then you have the singular points as you will for the elliptic locus. So in fact, now it seems that I think this actually leads to a proof. In the case when n equals prime, now you can extend everything over integral locus, but you can go much further. In fact, you can prove now with recent work with Christian Pauli, we understand the Hitchin fibration somewhat better outside the integral locus, and we managed to push this forward everywhere but over the origin, and then an independent argument will say that you can actually push it into the origin, and you will have a proof of topological mirror symmetry following the physics. So that was a quite exciting development. And the other interesting observation, which will conclude this lecture, is that if you take over the elliptic locus the soaptane topological mirror symmetry, and then in both sides you will have a decomposition. In one side, in the stringy side, you will have the decomposition into twisted sectors, the stringy contributions. In this side, you will have a decomposition into characters of the finite group, which will act on the SLN side. Then the refined version of topological mirror symmetry will say that these will agree term by term. And the surprising thing is that this geometrical observation, when reduced to a fiber, is nothing but Engo's main cohomological formula. In the case of for SLN only, his work is much more general, but topological mirror symmetry in a refined version is explaining exactly his formula. He has, of course, his own way to think about these shifts, but for us, these shifts which appear are exactly these fermionic shifts which appear in the stringy contributions for the PGLN variety. And then, of course, in his work, he takes this cohomological result. First of all, he proves it in positive characteristic, which is much harder. There are a lot of technical issues. But once he can do this, then the only thing he does, he then just compares the action of Frobenius of two sides, and then you calculate the traces, and then traces of those Frobenius will basically be these orbital integrals which appear in the fundamental lemma, and then this way we can use the fundamental lemma in the classical Langlands program, first in the function field case, but it's very lucky that it was known to imply the number field case. So let me finish with this point, with this amazing application by Engels of the Hitchin system, independently of whatever I said. So that's already a very nice application of an idea, namely the Hitchin system arising in mathematical physics, in fact coming from ideas from particle physics. And then the application is crucial in order to understand something which is very important in number theory. So I would like to finish with a quote from Atiyah. Before he received the Abel Prize, in an interview, he made this prediction that I would like to make a rash prediction that ideas from physics will have a big impact on number theory, as the ideas flow across mathematics, on one extreme number theory, on the other physics, and in the middle geometry. The wind is blowing, and it will eventually reach the farthest extremities of number theory and give us a new point of view. And indeed, so Engel's work is the first real example to this prediction, and then the good news is that his proof of the fundamental lemma is opening up the possibilities for many major results in number theory to be proven as we speak. So, thank you.